Hello, welcome to another module in this massive open online course on estimation for wireless communication. So far we are looking at the least squares cost function, and we have simplified the least squares cost function for the estimation of a vector parameter. We said that we have to minimize this least squares cost function to find the estimate or the maximum likelihood estimate of the vector parameter h bar, and towards this end we want to differentiate this least squares cost function and set it equal to 0. For the same purpose, we defined the notion of a vector derivative or a gradient, and we said for any function f of a vector parameter h bar, that is I have f of h bar dou f, that is the derivative d of this function, derivative of this function is simply given as the collection as the vector of partial derivative with respect to the components of the vector of partial derivatives with respect to the components of the vector h, correct. So, what we have over here is the vector derivative, and we also proved the property that if my function, that the partial derivative of c bar transpose h bar equals, or the derivative, that is this function c bar transpose h bar is equal to the derivative of this function h bar transpose c bar, which is indeed equal to the vector c bar. All right. So, this is the property that we have proved with respect to the vector derivative d with vector derivative df with respect to dh bar of the function f of a vector h. Now, let us look at another function which is termed as the quadratic form, and this is given as follows, that is, if I have a vector h bar, the quadratic form is defined as f of h bar equals h bar transpose p h bar, where matrix P is symmetric with P is a symmetric matrix, that is P equals P transpose. Now, if I have to differentiate this with respect to, that is considering the derivative of this function h bar transpose P h bar with respect to h bar. Now, I can do the following thing, this I can use here, I can use the product rule for the derivative. So, I can use the product rule for computing the derivative, and this is simply, therefore, the derivative of, well, the derivative of, this is simply, well, the derivative of h bar transpose, or first I treat h bar transpose as a constant, and therefore, this is the derivative of h bar transpose, derivative of, that is the h bar, that is treat h bar transpose as a constant and p h bar. Therefore, this is the derivative of, with respect to h bar transpose p h bar plus the derivative with respect to h bar of h bar transpose p, treat this as a constant, times h bar. So, basically this is your c bar in this instant, and this is your c bar transpose, and we have already seen the derivative of h bar transpose c bar is nothing but c bar. So, this is basically p times h bar plus the derivative of c bar transpose h bar is also c bar. So, this is basically h bar transpose p whole transpose, which is basically p h bar plus p transpose h bar, which is equal to P plus P transpose H bar, but we already, but note at this point, note that matrix P is symmetric, which means P equals P transpose. So, therefore, this is simply 2P times H bar. So, the derivative of the quadratic form H bar transpose P H bar with respect to H bar is basically 2P times H bar, and this is another result that we have derived, that is a vector derivative of H bar transpose P H bar with respect to H bar is 2P H bar for a symmetric matrix P, that is where matrix P is equal to P transpose. Okay. And now we have the results to basically differentiate the likelihood function, or simplify or basically the least squares cost function towards minimizing it, so that we can find the estimate of the parameter vector H bar. And we have already seen basically the least squares cost function can be simplified as, remember in the previous module we have already seen that the least squares cost function can be simplified as y bar transpose y bar minus 2 H bar transpose x transpose y bar plus H bar transpose x transpose x times H bar. And now if you look at this, let us treat this in this summation, let us treat this x transpose y bar as your vector C bar, and x transpose x, you can see this is a symmetric matrix. So, if this is P, therefore, if you call this as your function, if you treat this as your function H bar, remember this is the function we are interested in differentiating. So, df of H bar, where f is your least squares cost function, df of H bar with respect to dH bar is equal to, well, I have d of y bar transpose y bar with respect to H bar minus twice d of H bar transpose x transpose y bar with respect to dH bar plus the derivative of H bar transpose x transpose x H bar with respect to H bar. And now if you look at this, this quantity y bar does not depend on your H bar, is y bar transpose y bar. So, this quantity is basically 0. Now, this quantity is H bar transpose C bar. So, the derivative of this is equal to x transpose y bar, and this quantity over here is basically H bar transpose P times H bar, which means this derivative is twice P, that is twice x transpose x times H bar, which means the derivative now can be simplified as the derivative equals 0 minus 2 x transpose y plus 2 x transpose x H bar, which we are setting equal to 0. Remember, we have to setting derivative equal to 0 to find, we have, remember that is what we said, we have to differentiate this vector with respect to the vector H bar and set it equal to 0 to find the minima of this cost function, that is the parameter vector H bar, where the derivative is, where the vector derivative is 0, corresponds to the minimum of the least squares cost function, and that corresponds to basically the maximum likelihood estimate of the parameter vector H. So, basically here you are setting equal to 0 to 0 to find the minimum or the minima, let us put it that way, to find the minima of the least squares, that is your LS. Cost function, and this implies basically your 2 x transpose y bar is equal to x transpose x times h bar, and now you can see a beautiful relation which basically implies the minima occurs where h bar is equal to taking this matrix x transpose x h x transpose x inverse times x transpose y bar. Okay. So, this x transpose x, remember x is n cross m. So, this x transpose x is an m cross m matrix, square matrix, and if this is invertible, this is n cross, this is an m cross x transpose x is an m cross m square matrix, which means if this is invertible, I can take it on the left. Therefore, I have h bar equals x transpose x inverse times x transpose y. This is the value of h bar where the derivative of the least squares cost function is 0. Therefore, this is a minima of the least squares cost function. Therefore, this value of h bar minimizes the least squares cost function, and hence it corresponds to the maximum likelihood estimate. I am going to denote this by h hat. Therefore, the maximum likelihood estimate the maximum likelihood estimate h hat of the parameter vector h bar is h hat equals x transpose x, or let me write it a little bit more clearly with a different color to highlight this. H hat equals x transpose x inverse x transpose y bar. This is your least squares estimate, right. This is the ML estimate, also known as the least squares estimate, which in this case is also your LS estimate or the least squares estimate for the, this is also termed as the ML estimate, the maximum likelihood estimate of the channel vector h bar, or also as the LS estimate, where LS stands for least squares. Since we said this is the least squares cost function, this is also referred to as the least squares estimate of the channel vector h bar. Let us now look at another interesting property of this matrix over here. Now, if you look at this matrix over here, let us look at another interesting property of this matrix X, or this matrix which is a function of X, that is X transpose X inverse X transpose. This matrix is termed as a pseudo inverse. Pseudo inverse of X, and exists even if n is not a square matrix. This exists, the only condition is X transpose X has to be invertible. This exists also for non-square remember we have X which is the pilot matrix. Our X is basically, this is the pilot matrix, and this is an n cross m matrix, correct. So, this is a pilot matrix which is an n cross m matrix, and it is not necessary that n be equal to m, alright. We can have the number of pilot vectors or observations n greater than m. In fact, that would be desirable. We would like to have as many observations or as many pilot observations as possible. We would like to have as many pilot observations as possible. So, we can consider the case where n is in fact strictly greater than m, and therefore, what we are going to show now is, if you look at this matrix x transpose x inverse x transpose times the matrix x, where x is the pilot matrix, times the matrix x. Look at this, we have x transpose x inverse, we have x transpose x. So, therefore, this is equal to the identity matrix, correct. So, we have x which is not necessarily a square matrix, x is an n cross m matrix, where n is possibly greater than m, n is the number of pilot observations, m is the number of unknown parameters. So, ideally we would like to have n as high as possible, which means the vector x, the matrix x has a large number of rows, much more, that is the number of rows is much larger than the number of columns, all right. We can consider a scenario that n is greater than m. Remember, n is equal to number of pilot and m is equal to number of parameters in the parameter vector, that is your h1, h2 up to hm, and ideally we desire n to be greater than, that is n to be greater than or equal to m. And remember, when n is greater than or equal to m, our matrix x is n cross m, and this matrix is basically also known as a thin matrix, or colloquially this matrix is also known as a thin matrix, which means the number of rows is much larger than the number of columns. It is basically, it means that if n is greater than m, it is not a square matrix, therefore, x is not invertible or it does not have an inverse. Remember, inverse exists only for square matrices. So, if n is greater than m, then x cannot be, x is a non-square matrix, hence an inverse does not exist. So, for this then, for n greater than m, your inverse does not exist. However, if you look at this x transpose x inverse x transpose times x equals identity. So, this matrix this acts as a pseudo inverse, that is not an inverse, but acts as an inverse, that is known as a pseudo inverse, or basically also known as the left inverse of x, because when multiplied on the left, so when this matrix is multiplies x on the left, then you get identity. This matrix is also known as the left inverse. So, let us summarize that. I have this quantity this is also known as the pseudo inverse, or also known as the left inverse of your matrix x, all right. So, basically that is the least squares estimate. So, what we have derived is basically in this module, what we have looked at is a very important aspect of vector parameter estimation. Basically, we have differentiated, we have considered the vector derivative of the least squares cost function, set this vector derivative equal to 0 and found the value of that parameter vector h bar where this vector derivative is 0, or in other words basically where the least squares cost function achieves its minimum. That we have shown is basically given by x transpose x inverse x transpose y bar, where x is basically the pilot matrix, y bar is the vector of observations, and this we have termed to be the maximum likelihood estimate, since this corresponds to a minima of the least squares cost function. This is the maximum likelihood estimate. It is also, since it is also basically a solution that minimizes the least squares cost function, this is also known as the least squares estimate. There is a least squares estimate of the parameter vector h bar. Remember, the parameter vector h bar is the vector of channel coefficients corresponding to a multi-antenna. Remember, that is what we started with. It basically contains the vector of channel coefficients corresponding to a multi-antenna transmission scenario, where a base station is transmitting to a mobile, when the base station has m antennas, the mobile has a single antenna, and h1, h2, hm correspond to basically the channel coefficients of these m antennas. Right. So, basically this gives the least squares, or the maximum likelihood estimate of this parameter vector h bar, and this is also the maximum likelihood estimate. So, we will stop this module here and explore other properties of the maximum likelihood estimate in the subsequent modules. Thank you very much.